So I'm going to start off by first drawing a diagram so that you can see how to apply single slit into this particular scenario. So what we have is we have two parallel lines on a card. So I'm going to draw the card. And then there are two parallel lines. Okay, so these two parallel lines are actually like the two images we are trying to resolve. And I'm going to call this S1 and S2. It's like the two sources of light we are trying to resolve here. Okay, and then we are told that this is actually 2 millimeter apart. Now this two images, they are actually going to be formed at the back of my eye, but where's my single slit? Your eye actually acts like a single slit. So what is going to happen is your light is going to fall, and actually it's 5 meters away from the eye. So maybe I'm going to draw my eye here. Okay, draw the eye here. So the aperture of the eye acts like a single slit. So this is the eye is actually the single slit. Okay, the eye aperture is actually the single slit. Alright, and then of course the second line is actually also going to pass through the eye, and they are going to form an image at the back of my eye, which I register. Alright, now the question tells me that the distance of the card from the eye is such that the eye just fails to see the two lines distinctly. So it's at the point where it satisfies Rayleigh criterion. Just fail to see the two lines distinctly is the same as is just able to resolve the two lines. Alright, so this would mean that if one of the lines after passing through diffracts, and it will form a minimum, okay, where the image, the maximum of the second line forms. Alright, so it will look something like this. Okay, let's look at what the question wants. The question wants in part A to determine the angle that's subtended at the eye by the two lines. So what we want is actually this angle here. This is alpha. Alright, now if you look at alpha using trigonometry, you will see that we don't need to apply our single slit equation here yet. It's just basic trigonometry. This is actually a right angled triangle. So tangent alpha is actually, if I call this y and this is L, is actually equals to y over L. But if you look at the value of y and then L, this means actually the angle is going to be very, very small. So we know that using small angle approximation, when alpha is small, tangent alpha is approximately alpha. So alpha is approximately y over L. Putting in the values, we will get 2 millimeter, which is 2 times 10 to the power minus 3. And then your L is 5 meters. And that will work it out to be 4 times 10 to the power of minus 4 radians, which is your 0.1234 radians. What about part B? It says, by approximating the wavelength of visible light, okay, to be 500 nanometers. So that means that I'm going to take lambda to be 500 nanometer. I'm going to estimate the aperture of the eye. So the aperture of the eye, this is my B value actually. What is this value? So using our Rayleigh criterion, we know that your images are just resolved when the maxima from the second source actually overlaps with the first minima. So we are looking at the condition. This is where we apply our single slit. B sine theta equals to n lambda, where n is equals to 1. And what's my value of theta? If this is alpha, this theta here is also equals to alpha. So theta is equals to alpha. But we again know theta is very, very small. So we can approximate sine theta by alpha itself. So this will give me B times alpha equals to lambda. Alright, and B is what I want to find. This implies B is equals to lambda over alpha. And lambda is 500. Nano is 10 to the power minus 9. Divided, earlier on, I found my alpha to be 0.0004 radians, and that works out to be 1.25. If I work out and I convert into millimeters, 1.25 millimeter.